Let's continue on and learn more about propagation. We talked about the ionosphere. In the ionosphere, like I said, it's called ionosphere because it's the ionized particles around the Earth. So it extends up, I forgot, was it 600 kilometers, something like that? And it ends at a certain point because the atmosphere is very, very thin as you get farther and farther away. So there's less atoms to ionize. So the outer band, F2, uh, we call it, has a lot less particles or atoms in it, oxygen and nitrogen and stuff. So it isn't as heavily ionized as the F1 layer because a little closer in, it's got more atoms. And as you get closer to the Earth, there's obviously more oxygen and nitrogen, but less of the ultraviolet and gamma and other rays coming from the sun get through because they're being absorbed at the outer layer. So it's kind of there aren't as enough atoms out on the outer edge to get a very strong ionization. Where you have more atoms, you have less ionization. So it's kind of a weird effect. And we break these up into bands we call the D layer, the E layer, and the F layer. During the day, the F layer actually spreads out into the F1 and F2. How they measure these, I don't know. How they see a distinct difference between F1 and F2, I'm not sure. I just take them at their word. If you see in this diagram that on the night side where that shaded area is, that the F layer at night collapses back into a single layer. And the D layer basically disappears at night. So at night, you wind up with a very weak E layer and a single F layer, which is why propagation varies a lot between day and night.
The importance of this information, or actually this information will take on more importance if you decide to follow through and get your general, because then you'll have more bands available to you, and this affects what you can use at
Right.
different times of the
This
day.
affects the HF frequencies more than the UHF and VHF. So we talked a lot about VHF and UHF, and it's mostly line of sight. There are some modes where you can communicate over a long distance by using the E layer, okay? And you can have what's called sporadic E, where it doesn't actually refract, it reflects off of particles in the E layer, and it's not very predictable, which is why it's called sporadic E. But it does allow some, when it's working, some over-the-horizon signals in the 10, 6, and 2 meter bands, where 10 works the best during the day, particularly when you have high sunspot activity. And sunspots increase the amount of radiation coming from the sun. which is normally a good thing unless you get too much. Where it's a bad thing is when you have a CME, a coronal mass ejection, where a sunspot is basically a hole opens up in the outer surface of the sun and it lets more of the radiation out. A CME or coronal mass ejection is where it actually ejects material out of the sun and it goes off in different directions. And that one we had was it a month ago now? It turned out it missed us. If it had, because the sun's rotating, and when it ejected, it was getting close to going into the part of the sun we can't see. So it missed the Earth. Had it not missed the Earth, it would have been, I think, maybe the second strongest one that we've ever had. And it would have wiped out communications and possibly even affected the power grid. And we just had another one the other day that again missed us. One of these days is not going to miss. This is kind of showing that in the E layer where you can get some reflection off of particles in the E layer, which is why it's sporadic. And you can get some long distances there. They're showing what I'd say 1,200 kilometers more. This is just showing at different frequencies how waves are affected and what layers they get refracted off of. So at the lower frequencies, it turns out that's not always good because during the daytime, the D layer will absorb those really low frequencies, so they don't get refracted. They will work at night. You get a little bit higher frequency and you can get refraction off of the E layer or the sporadic E at the lower frequencies. It's really sporadic E when you're doing it at higher frequencies, which this doesn't show. And as you go on up in frequency, when you finally get up into the above 100 megahertz where you're in the VHF range, you can see they're basically going straight through the atmosphere. So which of the following types of propagation is most commonly associated with occasional strong signals on the 10, 6, and 2 meter bands from beyond the radio horizon? Did I hear a bravo?
Bravo.
Yep. Oh, that's up to 1,400 miles. Sporadically. I'm not sure why I stuck that one here. It's just showing some more of refraction off of the F layer.
Because it's interesting propagation phenomena.
Yeah, but I don't think we have a question on it anymore. It is showing a thing called NIVIS, which you see over on the left, which is called near vertical incident skywave, where if you have an antenna that is situated so it radiates almost vertically, you can get a short distance hop. And the reason that it's important is you notice over here for a normal antenna, it's what we call takeoff angle is going to be fairly low, in that case, 28 degrees. So it's going to go up, refract off of the F layer and back, and you're over here at what? I don't think they got the height, but you're, maybe a couple thousand miles. if you wanted to communicate with somebody 50 miles away, they're not going to hear you. It's right over them because they're on the other side of the horizon. So you can't do line of sight, and you're not going to get a refraction unless you do something like NIVIS. Unfortunately, we don't talk about NIVIS on the exam.
Yeah.
That comes into general or extra. So some of the other things you can do besides sporadic E is auroral backscatter. I think some people probably took advantage of that back here a month ago when we had the tremendous amount of solar radiation, and you could see the aurora down in Georgia and Tennessee.
Yeah, North Georgia and Tennessee, there were. That was a rare treat for them. I even went outside at 3 o'clock in the morning, but I've got way too much light pollution in my neighborhood. I would have had to get out in the 192 somewhere between here and Orlando would have been the best bet, but it probably wouldn't have been visible this far south.
But you can actually bounce signals off of the aurora, the northern or southern aurora. There's meteor scatter, where meteors coming through the atmosphere leave a cylindrical trail of ionized gas. It doesn't last for more than maybe a few minutes, but you can actually bounce signals off of those meteor trails. There's tropospheric scatter, where just particles in the atmosphere, the troposphere, which is the lower part of the atmosphere, actually scatters particles. So even though they're going straight through, some of the particles get scattered. You know, it's like dust particles and light reflecting off of them, same kind of effect. And then you have tropospheric ducting, where then the troposphere is basically the lowest portion of the atmosphere. If you have a temperature inversion, where you have a high temperature get above a lower temperature, that creates a duct, and it will actually refract signals. So you can send signals through that duct and they refract between, or reflect, however you want to call it, between that intersection of the hot and cold air and the earth and back, so you can get multiple hops. Like I said, in auroral backscatter, we're bouncing signals off the aurora. They're called the aurora borealis and the australis for the southern one around Australia. It's caused by the solar wind and solar flares. Like I said, we had a really big enhancement to the auroras when we had that extensive solar flares. It's kind of like sporadic E. It's not a very reliable because it's not a nice smooth aurora. The distribution of ionized particles varies greatly. So how it reflects or refracts is very different. You can even have kind of a multipath effect because of that. So you get distorted signals. This is just a picture of where the auroras normally are. And you see it showing up more at night than it is in the daytime. So what is the characteristic of VHF signals received via auroral backscatter?
Bravo.
Bravo. Okay, meteor scatter. Like I said, as meteors pass through, they leave an ionized trail. And particularly on the 6 meter band, if you're lucky, at the right time when there's a lot of meteors, you can bounce a signal off of one of those trails. Of course, you've only got a couple minutes to make some kind of contact. So I suspect, I haven't done it. It's probably pretty hard to do, but people do it. And you can get some long distances. So what band is best suited for communicating via meteor scatter?
Bravo.
Bravo. And just out of curiosity, what frequency would 6 meters be? Approximately. 300 divided by 6.
300 million meters divided by the wavelength. Should be
50 megahertz.
300 divided by 6. Yeah, the 6 meter band is 50 to 54 megahertz.
Yeah, I'm gonna practice it. Just to see if you're paying attention. All right, tropospheric scatter. In the troposphere, it says it's in the 6 to 10 kilometer range. It's the lowest portion of the atmosphere. You can get some scattering on UHF and SHF frequencies. That's super high. That's the 3 gigahertz and above. And it's kind of random scattering like you would see on sporadic E. And I think there's a little picture here which kind of shows it better, where your normal signal is going to go straight through, but you get a little bit of scattering. So it's only a small portion of the signal strength. And it's off in all different directions. So it's going to be a very weak signal at best. And then we have tropospheric ducting, where if you have an inversion layer, where you get a layer of cooler air. Did I get it backwards before?
Well, the farther you get away from the
Oh, yeah.
air, the cooler
The warm air is on top of the cool air, which is not normal.
Yeah.
That interface between the warm and cool air, and I don't understand the physics of it, but it tends to refract or reflect. I think in this case, it's more of a reflection instead of actually bending it of radio waves. And it forms what we call a duct. So that signal can kind of bounce between the earth and that interface multiple times. Of course, every time it hits the earth, it's going to lose some of its energy. So that limits how many times it can actually bounce. There's just another example of showing that interface. And I guess in that case, they're indicating it is refraction, because at certain angles, it's still going to refract, but it's not going to make it back into the duct. So what type of propagation is responsible for allowing over the horizon VHF and UHF communications to ranges of approximately 300 miles on a regular basis?
Alpha.
Well, let's see. By George, you got it right. What causes tropospheric ducting?
Delta.
All right. Okay, we talked about absorption before, and precipitation is water. Rain, snow, ice, all those things. So they absorb microwave signals. They have very little or no effect on HF frequencies below 30 megahertz. Above 30 megahertz, they start having some effect. And the higher the frequency, the bigger the effect. This is a plot I found of vapor absorption versus frequency, and you can see, and I don't exactly understand the green one, but the other two lines are the normal absorption rates as you go up in frequency, and these are all in gigahertz. They're up in the microwave range. So you can see, and that notch there, I believe, is either oxygen or nitrogen absorption band, something like that. That has a nonlinear effect. What weather condition might decrease range at microwave frequencies?
Charlie.
Charlotte. What's the effect of fog and rain on signals in the 10 and 6 meter bands? So 10 is how many megahertz?
30.
30. And 6 is, we already did that one, 50.
50. Yes.
Okay, so it should have a little effect because it starts having effect at 30. Okay, so we learned about sporadic E that was on the TICS 10, 6, and 2 meter bands where you can get some over the horizon. Doing auroral backscatter, doing meteor scatter on the 6 meter band. Tropospheric ducting because of the inversion layer where you can get a refraction, and that precipitation absorbs the higher frequencies, 30 and above.